Dr. Fred DePiro, and this video is about some foundational material, Kirchhoff's voltage law and Kirchhoff's current law. Learning objectives include forming equations using these laws for voltage and current, and applying these laws in order to solve for unknown quantities. We refer to Kirchhoff's current law as KCL and Kirchhoff's voltage law as KVL. Prereqs are Ohm's law, passive sign convention, and the ability to identify nodes and meshes in a circuit. Okay, so why do we need this? KCL and KVL form the basis for circuit analysis. They establish relationships between voltages and currents that are true in any circuit. They permit formulation of equations that describe a circuit and then allow us to solve for unknowns. These are as foundational as F equals ma is to statics and dynamics. Take a second and think, can you describe KCL in words, perhaps based on prior exposure in a physics course? Here are some possible examples. Sum of the currents into a node equals 0. Sum of the currents out of a node equals 0. Sum of the currents into a node must equal the outgoing currents, innies equal outies. Here are some other similar statements. Nodes don't accumulate charge, or in terms of the water analogy, the pipes don't leak. So let's try KCL, Kirchhoff's current law, in a specific case. As a review, there are 3 nodes in this circuit. You see this bottom node here. See this top node, like a left corner, and then there's a T-shaped node here. These nodes are numbered 0, 1, and 2, and node 0 is highlighted in red on the bottom here. We predefined current directions for the elements that are connected to node 0, and in this case, we'll sum currents into the node. We have I2, I8, and I1. Summing into the node and using the defined current directions, we have plus I2, plus I8, minus I1 equals 0. The minus came in there algebraically because we were summing into the node and the predefined direction was going out. For a numeric example, try finding I8 given that I2 equals 2 amps and I1 equals 3 amps. You'd find I8 equals 1. There are a lot of variations to KCL. We can sum into the node as we just did. We can sum out of the node. Okay? Algebraically, we would get the negation of each of the quantities in the prior example if we were summing out of. And equating innies to outies is another convenient way to do it. You just work with the current direction arrows the way they're given in a current problem. I2 and I8 are going in. I1 is going out. Innies equal outies. Easy. Now, if you're in a situation and let's say you wanted to sum currents into the node and you had one of the current arrows that was predefined to go out. This can happen. Okay? Don't let that bother you. If you would like to have simpler algebra where you're summing all of these, fine. Define a new current, turn it around, define IA going into the node, and then algebraically these are all added. That's perfectly fine. Okay, moving on to Kirchhoff's voltage law. It applies to voltages going around a mesh, and I use what I call Monk's style. That's Mr. Monk from the TV show. And when I say I'm being like Mr. Monk, what I mean is that's shorthand for I'm being brutally systematic and consistent. When I'm given a choice, I'm always going to take the same option. Here's an example. I'll always do KVL clockwise. That's not too unusual. There are some textbooks that are written where every single circuit is analyzed with KVL. It's clockwise. Okay? Just trying to be systematic and avoid making sign errors. Okay, so what you see here, first of all, is this little graphic which indicates passive sign convention as a reminder. Here are some steps that we'll follow in order to do Kirchhoff's voltage law. Notice that some of these options are choices versus others are required. I'm going to choose to define the current direction as clockwise. I'm going to choose to apply KVL following the direction of my defined current, clockwise. However, I then must use passive sign convention to assign polarities. Don't have a choice on that. That ensures conservation of energy. Lastly, when I form an algebraic equation associated with each term going around the mesh, I'm going to choose to either add or subtract based on which polarity I encounter first. If I hit the plus sign first for a defined polarity, I add. If I hit the minus sign first, I subtract. So I'm going to choose to define the current direction as clockwise, as you can see with I1 here. Then a question would be, as I use passive sign convention going around this mesh, should the plus polarity, for example with a 3 ohm resistor, should that plus sign be on the left or should that be on the right, following passive sign convention? Okay. The plus sign for the 3 ohm should be on the left, on the top for the 2 ohm, to the right for the 1 ohm. Mr. Monk starts doing KVL at 7 o'clock. Here we go. Going clockwise, following the direction of the derived current. First thing I hit is the minus side of the 12 volt source. So I start off by saying minus 12. Continuing around, I hit the plus sign for the 3 ohm, so I have 3I, then 2I, then plus 1I. I've made it around the loop, so those sum to 0. Solving that, you get I equals 2 amps. No surprise. Okay, so in this video we talked about Kirchhoff's laws. These are foundational for us. They allow us to form equations to solve for voltages and currents. We talked about Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL.